So notice we've got these two blocks, and it's sort of a modified Atwood top machine setup. The string, negligible mass, which is usually going to be the case in Physics 1. The magical massless pulleys with no friction. And we know in the real world, none of that's really true. The pulleys have mass. There is some friction, but we're ignoring those things to make the math easier. And that's the way it's usually going to be in Physics 1. So it says the mass M2 of block 2 is greater than that of block 1, and we're going to release them both from rest. So you guys, I hope, realize that if this mass is a little bit bigger than the other one, then it's going to start to fall this way, which means this one's going to get pulled up. So part A asks us for a free body diagram. On every AP Physics 1 exam, you're going to see 1, 2, sometimes more free body diagrams. These should be free points for you. You got to get the free body diagram points. So let's look. Also notice that it says to draw the forces, not the components. It also gives you some lines, which tells me that I probably want to draw those forces at least somewhat to scale. They don't have to be perfect, but try to draw them so that the length has something to do with the magnitude. So let's look at block 1. So if you think about block 1, we really have two main forces acting on that block. Someone unmute and tell me what the forces are that we need to show in our free body diagram for block 1. Don't be bashful. If somebody tell me block 1, what are the forces we need to show?
Force of tension going up.
Yep.
And then force of weight, or mg, going down.
There you go. So, and in this case, which one of those is going to be larger?
In this case, force of tension is going to be larger for block 1.
Right, because we know that block's going to be moving up, right? So I'm going to draw. I'm going to draw the force of tension, and I don't really know how long to draw it. So I'm going to draw it like this, and I'm going to label it F sub T. That's sort of the standard way of labeling tension. You probably could get by with a T, but that could be torque, that could be other things. So F sub T is probably the best way to do it. When you're doing weight, you probably could get by here with just a W. You probably could get by with an FG. But what I would recommend that you do when you're doing weight is go ahead and do it like this. And I'm going to write it as M1 times G. That's what weight is, right? Mass times gravity. And notice that I drew that arrow a little bit shorter than I drew the tension arrow. We want to do the same thing for block 2. With block 2, though, we know block 2 is going to have a net force down, which tells me that its weight is going to be bigger than the tension. And we know that its weight's also bigger than this M1G line. So let's draw it longer. And that's supposed to be a straight line. It's not perfectly straight, but close enough. Whoops. So we're going to label that one as M2 times G. And we also need to draw the tension in. And this tension is going to be the same throughout the rope, or at least pretty close. So I'm going to draw it the same length as the other one, label it FT. So easy points there, hopefully. Any questions on the free body diagram? All right, another thing that's on every AP exam, more so recently than in years past, are these derive equation kinds of questions. Last year's exam, I think, had 2 of these. There's going to be at least 1. We're looking to derive the magnitude of the acceleration of block 2, and we want to express our answer in terms of M1, M2, and G. Those are the only variables that ought to show up in that equation when you get through with it. Everything else ought to cancel out. So there's a couple of different ways that we could do this, but I would recommend that you start with an equation. I'm going to start with this one. I'm going to start with F net of the system. The system's the whole picture, right? Is equal to the mass of the system times the acceleration of the system. And like I said, there's 2 or 3 different ways we could work this one. This is the way I'm gonna go about this one. So how could I get the net force acting on this system? What's the net force going to be equal to in terms of an equation? Anybody have an idea? What's causing this system to move? The difference in what 2 forces? Don't be bashful. The difference in what 2 forces is causing this system to accelerate?
Gravity on each block?
Yeah, the weight of each block. So I'm for my F net, I'm going to go M2G minus M1G. Everybody with me that that's the net force, the difference in those 2 forces. I'm going to erase my free body diagram here just so I have some white space to work. So that's equal to the mass of my system, which is going to be the mass of 1 plus the mass of 2 times the acceleration of the system. All right, and then to solve for the acceleration, I'm just going to divide both sides by M1 plus M2, and I'll end up with this. Now notice it asks for the acceleration of block 2. What do we know about the acceleration of block 1 and block 2 in this setup? They're the same, right? So this answer works. You could have factored this out a little bit. You could have factored out a G up here if you wanted to do that. So you could have written it as M2 minus M1 G over M1 plus M2 equals A. That would have worked. And you could have went about this a completely different way by essentially working out free body diagram type questions for each one of these. For example, I'm not going to work the whole problem this way, but let's just take block 2 for a second. Think about the forces acting on block 2. So I'm going to say F net on block 2 is equal to the weight of block 2 minus the tension. And I could do the same thing over here for block 1 and say that F net on 1 is equal to the tension minus the weight of that block. I could solve for T in one of these equations, whichever one I needed to solve for, and then substitute that into the other equation and solve for acceleration that way. So 2 completely different ways of working the problem. You'll get the same answer either way you do it. Question so far? These derive equation questions intimidate a lot of Physics 1 students. But if you'll take a basic equation, start with that, and just work step by step, you'll get there. Notice that my final answer is only in terms of the 3 variables that they told me to have. M1, M2, G. You need to make sure that's true at the end of the problem. All right, let's look at the next part of this question. So take a minute and read through this one. This one's pretty straightforward, but everybody take a minute and look at the picture and read it. And in about a minute, we'll talk about it. So the only thing that changed in this part of the problem from the first part is that we added block 3 up here on the table. Now, if we think about a free body diagram for block 3, we know that the weight of block 3 and the normal force on block 3, those are canceling each other out. So essentially, this is not affecting the force acting on the system, but it is affecting the mass. And we know mass is really just another word for inertia. So if we have more mass, but the same net force, and we think to Newton's second law, so if this goes up and this stays the same, then the acceleration is going to be less. So first of all, you need to say smaller. But notice, explain. Sometimes they might say justify. It doesn't take a lot of writing, just a sentence or two. And all you really need to say here is, because the system now has more mass and the net force is unchanged, the acceleration is going to be smaller. That's all it takes. One good sentence, maybe two. And that's it for the first question. I'll show you what the scoring guidelines for it look like. Maybe. Let's see if I can blow that up a bit. So here's how you earn points. Part A was worth 2 points. That was just for getting each of the free body diagrams correct. And you can see those look pretty much just like the ones we drew. They actually wrote out the word tension. That's okay. We did F sub T. So here's how they worked out the derive equation problem. Notice they used the second method that I described for you. They solved for, they essentially used the free body diagram to come up with equations for each block, solved for T in one of the equations and substituted into the other. Notice that this part of the question is worth 3 points, and that you got points for each step along the way. So even if you don't get to the right answer at the very end, you can still earn some credits for showing your work. So that's what I'm saying. Start with a very basic equation and start solving toward what you're looking for, and show all that work step by step, nice and neat, and at least you'll earn some credit along the way. Let me shrink this down again.
Mind if I butt in for a second?
Not at all.
All right, quick pointer about free body diagrams. Every single free body diagram on the physics exam has the same directions, that the arrows have to start on the dot, point away from the dot, and be labeled. If any of those things are not happening in your diagram, you will not get points. So if your arrow is floating near the dot but not touching it, you're not going to get points on that diagram.
Yep. And little picky things like that will get you. So that's really good advice.
They give you a big dot, use it.
Yep. Notice on the screen now, here's the solution that I used first for that first problem, to use the net force of the system and work it out that way. And then finally on part C, that was worth 2 points. So you had to say the acceleration of the new system with that added block was smaller. You got a point for that. And then in some way or another, talking about the fact that there was more mass and therefore less acceleration. More mass, more inertia, something like that. All right. Any questions for me on the first problem? All right. So the second problem is going to be one of the design and experiment kind of questions. Always going to be one of these on the exam. And I've found that students aren't always very good at these. Because number one, you got to give some detail, not a lot of detail, but it's telling you in this question some specific things that have to be included in your answer. If you don't include those, you're not going to get the point. So take a minute and go ahead and read part A and subparts 1 and 2, and then we'll just kind of talk our way through this one instead of taking time to write it out. All right, so we're looking for the coefficient of static friction between a long flat wood board and a small wood block. And we've got to describe an experiment for determining that coefficient of static friction. Assume equipment found in school physics laboratory is available. Typically, when they give you a question like this, you only need really simple things like a ruler, a protractor, maybe something to measure mass with. They keep it really simple. I mean, if there's something you don't know how to measure, you probably could get by with saying use your smart cart to measure it or something like that if you just don't know how to measure something. But typically, they're pretty easy things to measure. So part A says to describe the experiment for doing this. And notice that along the way, we've got sort of some advice for how to do that. So it wants us to draw a diagram indicating each quantity that we're going to measure and how we're going to measure it. So we got to get both of those things. And then we're going to describe the overall procedure to be used. And we're going to include any steps to reduce experimental uncertainty. That's going to always be part of this question. And really, what's the main thing you ought to talk about if you're trying to reduce experimental uncertainty? Somebody unmute and tell me how you could reduce experimental uncertainty. Don't overcomplicate it. What do you need to say?
Maybe you could repeat I was going to say you could probably try repeating the procedure multiple times.
Exactly. Run multiple trials. And we'll talk a little bit more about that when we get to our setup. But the main thing is lots of trials. Do it more than one time. All right. So here's the way that I'm going to approach this. And there are other ways you could do it, but I'm going to start with my diagram. So I'm going to start with my board, and you probably should label these. So this is my board. And then I'm going to put the block on the board. And we're going to say this is the floor right here. This is my block. And I'm going to label that theta, some angle. So the way that I'm going to do this is I'm going to slowly raise up that board and increase this angle right here until that block just starts to move. At that point, the parallel component of the weight is essentially equal to the frictional force. But before we get there, let's think about the frictional force stuff. It's always good when you're doing these experimental design questions to really start with an equation in mind. And you got your formula sheet, that's going to be handy. This is going to be the only formula on there that's going to make much sense for guiding your work on this particular problem. So it's the force of friction is equal to the coefficient of friction times the normal force. All right, so I've got my diagram. I've labeled everything. Now I need to talk about what I'm going to measure and what equipment that I'm going to use to measure it. I'm really only going to measure two things. I want to know the mass of this block. And actually, I think I could get by without even knowing the mass of the block. But I'm going to measure the mass of the block, and I'm going to measure that with a balance. You could use a triple beam balance, or you could just say a scale. And then I'm going to measure this angle. And I'm going to use a protractor to do that. All right, and again, my procedure is going to be start with the block on the board, level with the ground, and then slowly increase the angle, raise up the board and increase the angle between the block and the floor until the block just starts to slide. And at that point, this relationship is going to be true. All right, so the other thing that I want to mention while we're here before we go to the next part, reduce experimental uncertainty. Let's say that number one, that we repeat and do this at least 5 or 6 times. You could move the block to a different part of the board also. Maybe you move the block up higher on the board. Maybe you move it lower on the board. And then you do multiple trials there too. All right, I think we've covered part A. Questions so far? All right, so let's look at this part then. So part B, derive an equation for the coefficient of static friction in terms of quantities measured in the procedure from part A. Now, I think I would have hated to have been one of the people trying to grade this question, because I can only imagine the procedures that some kids came up with. And if it was a valid procedure, how they derived that equation probably could have been all over the place. But for what I did, let me redraw my picture here. I'm going to take my block and I'm going to draw in some forces and some components of those forces. And that's terrible. Let's see if I can make that a little straighter. So that's going to be my weight, mg. I'm going to take that and break it into components. And I'm going to break it into one component that is, this is not an ideal setup for drawing, so bear with me for a minute. One component that's supposed to be perpendicular to the surface, and then another component that's parallel to the surface. I'm lagging. There we go. So I'm gonna write this as F. This is a symbol for perpendicular, and this is F parallel. When you do components on an incline like this angle right here is going to be the same as the angle of your incline. So let's think for a second. I started with this idea that when that block starts to move, this ought to be true. So let's see if I can come up with some equations to illustrate this a little bit better. So F parallel, let's give that in terms of mg. So I've got an angle right here. F parallel is the side opposite of that angle. And then mg is the hypotenuse of my triangle. So I'm going to say sine theta is equal to opposite over hypotenuse, like that. And that's going to give me, if I rearrange just a bit, this relationship. And I'm going to plug that in right here. All right, friction we know is mu times n. But I can take that down a little bit further. Because remember, this is supposed to be in terms of things that I measured. And the only things that I measured were the mass and the angle. So I need to get rid of everything else if I can. So I'm going to make some space for myself here. we know that in the normal force, and I wish I need to redraw my picture real quick. The normal force is equal but opposite to this perpendicular component of the weight. So I'm going to find that perpendicular component of the weight by using cosine. And I'm going to say the cosine of my angle theta, which is right here, is equal to that adjacent side, which I'm going to call F perpendicular, over my hypotenuse, which is the weight. So F perpendicular is equal to mg cosine theta. So I'm going to go back up to this equation for where I have FF is mu n. Now I'm going to plug in, for n, I'm going to plug in mg cosine theta. Notice that I've got mg on both sides of the equation. Those can cancel. So now I have mu cosine theta equals sine theta. I'm going to divide both sides by the cosine of theta to get. That would be a perfectly acceptable answer. You could also write that as tangent of theta, because sine over cosine is tangent. So that's the kind of thing you want to show when you're deriving your equation. Takes a little work, takes a little time, but if you show all that, you're going to get 3 points or whatever this part of the question happens to be worth. All right, questions there? That's probably the hardest part of the problem. The next two parts should be pretty easy. I want you to take a minute and read part C and part D. And for part C, you're going to need to look at the chart. So go ahead and do that now. All right, so for part C, based on the data in the table, the students want to test the hypothesis that the coefficient of static friction and kinetic friction are equal. Now, first of all, I hope you know that typically, almost always, static is going to be higher than kinetic. That's just something you ought to know. But we need to base our answer on this data. They have the same average. So some people would probably be very tempted to say they're equal. But if you look a little closer at the data, what should you really be paying attention to? Somebody help me out. What in the data should stand out to you? Come on, yo, you guys are out there. Which lab group's data should you really pay attention to?
There's a skewed trial on 5.
Yeah, so lab group 5 is that lab group that every teacher always has in their class that finds a way to mess up every lab. And they really mess this one up. Notice how different their numbers for both kinetic and static friction are. Everybody else is close. If you averaged 1 through 4 and 6 together, you'd get about probably 0.44 or so for kinetic friction. And if you average the coefficient of static ones together, you'd probably get about 0.54, maybe somewhere in that neighborhood. They're all really close, but these guys did something wrong. So my answer here would be number 1. These guys are not equal. And notice it asks us to justify. What do we call, what's a good word for data points that are just way, way out there?
An outlier.
An outlier. That's a good word. And you if you don't know the word outlier, you could just say lab group 5's numbers are crazy or something like that. That'd probably be okay. But a better way of saying it is that the data points for group 5 are outliers. They are not anywhere close to the numbers that the other folks in the group got. And if you take out those numbers, these averages are going to be different. I would probably go ahead and average them without those numbers in there and say the new averages without those numbers are. I don't think that's necessary to get the point in this problem, but I would do it just to be on the safe side. Any questions there? All right, last part. A metal disc is glued to the top of the wood block. The mass of the block disc system is now twice the mass of the original block. Does the coefficient of static friction between the bottom of the block and the board increase, decrease, or remain the same when the disc is added to the block? Somebody tell me what you think.
Stays the same
And why do you think that?
because mass would affect force normal, but the coefficient is independent.
So the coefficient really is a measure of how two surfaces interact with each other. It's independent of the mass. It's about the surfaces. So your answer is exactly right. Remain the same. And I would just say that the coefficient of friction is independent of mass. It measures how two surfaces interact. Now, they also took a different answer here. They also took decrease in their scoring guidelines. How could that be true? And by the way, the best answer is the one he just gave. That's the one that you ought to give. But how do you think they justified taking decrease? What did you have to say in your reasoning to make decrease work? Anybody have an idea? What they essentially took is if you put more weight on it, what's going to happen to the surfaces after they slide just a little bit? Since we're talking about probably wood, maybe soft wood, what's going to happen if you have heavy things, heavy wood pieces sliding on each other?
They would smooth each other out, kind of like sandpaper.
Smooth out, right? And so they took that answer. That's not the best answer. The best answer is remain the same because the coefficient of friction doesn't have anything to do with mass. That's the best way to answer this question. But they did take decrease if you explain, and only if you explain that when the surfaces rub together, that there could be some smoothing going on. All right, any questions on this one? You got to take your time on these design equation problems. Like I said, before you start, I would find an equation on the formula sheet and use that equation to guide me through the whole problem. If you have the right equation, it's going to tell you the things you need to measure. Hopefully you know how to measure them or what to measure them with. And it's going to guide you through the derived equation part of the problem as well. Typically, C and D usually are pretty easy. The hardest parts to me of these kinds of problems are A and B. C and D usually pretty straightforward. All right, let's look at one more. Actually, I think we got two more. So this is another modified Atwood machine kind of problem. Take a minute and just read it, and then we'll work through this first part at least together. All right, so look real closely here on part number 1. The mass of block A is much greater than the mass of block B. Estimate the magnitude of the acceleration of the blocks after release. So let's think of this as if A is this huge, big old block up here, and B is a little bitty tiny thing. Somebody tell me what you would estimate the acceleration to be if that was true. If A, let's think of A as like a concrete block and B is like a feather.
0.
Near 0. So probably get a point for saying that. The acceleration is going to be near 0. But then notice you got to explain your reasoning. And notice it says without deriving or using an equation. They want you to actually use some words here. So I would say the acceleration is going to be near 0 because the mass of block A is much greater than the mass of block B. And therefore the net force acting on the system is near 0. That's really all it takes. Now notice part B is the opposite. Part B, or part 2 rather, block B is now the huge block, and block A is a tiny, tiny block. So if that were the case, what would be a good answer for the magnitude of the acceleration of the blocks? If B is really, really big and A is tiny, what would be
9
a good?
to 10.
Say again.
Like 9 to 10.
Yeah, so it's going to be right around G, right? So I'm going to say the acceleration, since we always use 10 in AP Physics 1, I'm just going to say it's going to be somewhere around 10. And the answer would be, your explanation would be that B is essentially doing what? When you let B go, it's essentially in free fall because there's almost no mass on the other side. And because there's no mass, what already told us there's no friction. So there's essentially no force holding that thing back. And that's really all it takes. Very, very sweet, to the point, one good sentence. I think you could get by with saying that block B is essentially in free fall because its mass is so much larger than that of A. All right, so that was the word part. Now we're going to get to a numerical part of this this problem. Well, not quite yet. So here's another free body diagram deal. Now suppose neither block's mass is much greater than the other, but they're not necessarily equal. The dots represent block A and B. On each dot, draw and label the forces, not components, exerted on that block after release. Represent each force by a distinct arrow starting on, and notice, starting on and pointing away from the dot. So there's what Ms. Simons pointed out to you a second ago. So for block A, what forces should I be showing on my free body diagram? Block A. Somebody help me out. Well, I'm going to tell you there's 3 of them. What are the 3 that I should show?
You would have force of weight going down,
Yep.
normal force going up,
Yes, sir.
and then force of tension going to the right.
Perfect. So let's go over here and draw that. So force of weight, like I said, it's a good idea when you're doing the force of weight just to write it like this. So mass of A times G. The normal force in this case, since it's sitting on the table, how long should we draw the normal force arrow?
Same length as the MG arrow.
Right. They should cancel each other out. So same basic length. I don't have any lines here. I don't think the readers are going to pull out a ruler and measure. Just make them as close as you can. I'm going to label this F sub N. That's the best way to show the normal force. And then the other one we ought to show is the tension. And we know for block A, the tension's going this way. And again, F sub T, the best way to notate that. Now let's go back to our picture for a second. So for block B, we really only got two forces we need to worry about, right? The weight and the tension. So for block B, for weight, I'm going to go MBG. And my tension force for block B is acting up. Maybe something like that. And that's it. Notice that my arrow started at the dot and pointed away from the dot. And also, you got to make sure you label everything. You got to label those forces. If you do that, you're going to get the point. All right. So we're back to another derive equation question here. So derive an equation for the acceleration of the blocks after release in terms of MA, MB, and physical constants as appropriate. If you need to draw anything other than what you've shown in part A to assist in your solution, use the space below. Do not add anything to the figure in part B. So if you want to get points for something, it needs to be drawn in the space where your answer is supposed to go. The reader may not go back to the diagram that was in the prompt. They're looking in the space where your answer is supposed to be. That's going to be laid out for you. So if you're going to draw a diagram, that's where you should draw it, is in the answer space. So let's look at the diagram for a second. I'm going to go back to the picture for a second. So I'm trying to derive an equation for the acceleration of the blocks in terms of the mass of A, the mass of B, and physical constants. So I'm going to work this one very much the same way I worked the very first problem. I'm going to work it in terms of the system, and I'm going to say the net force acting on this system is equal to the mass of this system times the acceleration of this system. In this case, since there's no friction, and since block A is sitting on the table, the net force acting on this system is the weight of block B. So my net force is going to be MBG, like so. And that's equal to the mass of the system, which is the mass of A plus the mass of B times the acceleration of the system. So to solve for acceleration, I just need to divide by the stuff in parentheses. So my acceleration is equal to MBG over MA plus MB. And if we go back to the prompt for a second, remember it said in terms of MA, MB, and physical constants, which in this case would be little g, is a physical constant. So if we look at my equation, the only variables that I have in there are MA, MB, and a physical constant, in this case, G. Questions? All right, well, let's finish this one up then. So consider the scenario from part A2 where the mass of block A is much less than the mass of block B. Does your equation for the acceleration of the blocks from part C agree with your reasoning in part A2? So let's go back to my equation. So remember, we're saying in A2 that block A is really, really tiny compared to block B. So let's say that A is almost 0. let's just make it be 0. So where I've got MA in my equation, I'm going to plug in 0. So if I put 0 there, notice that MB and MB can cancel out. So my acceleration is G. So if I were working this problem, I would show what I just did, and then I would annotate that work. I would say if the mass of A approaches 0, the mass of B cancels out on the top and bottom of my equation, leaving the acceleration equal to the acceleration due to gravity. And just make sure that you say, mark the yes, and then explain. I think the trickiest part of this equation, or this problem rather, is part E. So take a minute and read part E and see if you guys can come up with an answer. I'm going to give you about 2 minutes to read it and formulate your own answer. So I'm going to go back to the picture for a minute. So what this is saying is that to begin with, we've got one of these magical massless pulleys. And in that case, when that massless pulley is there, the tension in this rope, they're calling it T1. But then we replace the pulley with a more realistic pulley, one that has mass. And when that's put in there, this tension is now called T2. We'll say with mass. We'll call this with no mass. So the easiest way to think about this problem, I think, is to think about what's going on with the acceleration. When the pulley's massless, well, when there is extra mass due to the pulley, what does that do to the acceleration of the system? When the pulley now is counting as mass, but the forces are not changing, it's, at least the net force on the system is not changing, what happens to the acceleration of our system? Somebody help me out.
The acceleration will decrease.
Acceleration will decrease. So that's where you got to think. Let's just think about a picture of just block B for a second. This is block B. We know that for block B that we got the weight going down and we've got the tension going up. And we know that when we add this pulley with mass, we know that its acceleration has to go down. So think about it in terms of an equation for a minute. So I'm going to say F net on B is equal to MBG minus tension. Let me write that a little better there so it's easier to see. Which means the mass of B times the acceleration of B, something like that. So we're saying that if the mass of the system goes up, and this might not be the best way to show this, but if the whole mass of the system goes up, this acceleration has to go down. And the only way that acceleration can go down is if what happens to that tension. The only way B's acceleration is going to be less is if what happens to the tension. Somebody help me out. We know that's not changing. The mass of B is not changing. We know the acceleration of gravity is not changing. That means the tension's got to change. And what's got to happen to that tension to make the acceleration of block B be less when there's that massful pulley? The tension's got to go up. And I think that's counterintuitive for some people. But the best answer here is that T2 greater than T1. And the way that I would explain it is maybe you do a better job on paper than I just did there orally. But for the acceleration of block B is going to become less because the pulley adds mass to the system. And the only way for the acceleration of block B to be less with the massed pulley than with the massless pulley is if the tension increases. Tammy, you have a better way of explaining that? I know I fumbled around with that.
There's another way that I look at that.
Okay.
So as soon as they say that the pulley has mass, we've changed the problem from just an Atwood machine and forces to rotation.
True. Yep.
Ignore the blocks. The blocks haven't changed.
Right.
The rope hasn't changed, but the pulley changed. So now we have to look at the rotation of the pulley. And in order for that pulley to spin, there has to be a torque.
Mm-hmm.
So there's a rope coming across the top from the block sitting on the table, and there's a rope hanging off the side for the block that's hanging there.
Yep.
They're each creating a torque. If those two forces, those two tensions are the same, then the pulley does not spin because they're pulling in opposite directions.
Yes.
But the pulley does spin, and it's spinning with block B towards the ground. So that has to be a bigger force in order to win.
I like that. Very good. Let's see what they said on the rubric there. All right, it's looking like the way that I spaced this guy really messed that up. So let's see. Yeah, that's going to be unreadable. We'll skip over that. But either one of those explanations, I think, would be fine for the points. Let's end with one more quick problem. Take just a minute and read through part A, and I think we can do this one pretty quickly. All right, so we're on free body diagram once again. So at first, somebody, let's just say they struck it. So let's say they kicked the block, and the block is scooting up the ramp. And we want to show the forces acting on the block up the ramp and then on the way back down. Notice it says as it is sliding. I noticed on mock exams when we were grading those, a lot of the students wanted to include that initial force on their free body diagram, like the push that got this thing going. If this box is already sliding, that force is not there anymore. You don't need to show that. You need to show essentially three forces here. And those forces you need to show are number one, the weight, which we want to draw straight down and label that as just mg or weight. We know there's going to be a normal force, and that's going to be perpendicular to the surface. Maybe something like that. And then the other thing we need to show is friction. We know friction is always in the opposite direction of motion. So if this block is going up the ramp, that means the friction is acting down the ramp. So maybe something like this. Everybody with me on the free body diagram going up? All right, one going down is going to look very similar. So weight, normal force, but in this case, the block is moving down, which means friction should be acting up. So friction ought to be going this way. Something like so. So part A, I think, was pretty straightforward. The tricky part of this question is part B. Take a minute and read part B. And just, you don't have to write down an answer, but just think how you would answer this as you're reading through the question. I'm going to bet a lot of you are tempted to go here. That's not the right answer, though. The best answer here is that one. And here's the reason why. Think about it in terms of these free body diagrams. As this block is going up, you've got not only friction acting against its motion, but you also got the parallel component of the weight also acting down the plane on it, which means there's a pretty large net force. And that means there's going to be a pretty large acceleration. And it's going to quickly accelerate to zero. It's going to go up and stop. On the other hand, when you're going down the ramp, you've got friction acting against the motion, but the parallel component of the weight is acting with your motion, which means the net force is going to be smaller, which means the acceleration is going to be smaller, which means it's going to take it longer to get to the bottom. So the way I would answer this, number one, choose this answer. Time down is greater than the time up. And then I would talk about the net force acting on the block in each direction. And I would say on the way up, because you have friction and the parallel component of the weight opposing the upward motion, you've got a large net force and therefore a large acceleration. And very quickly, the velocity gets to zero and it gets to its highest point. On the way back down, because friction and the parallel component of the weight are acting in opposite directions, the net force is smaller, the acceleration is smaller, which means it takes longer to cover the same distance than it covered on the way up. Another way of saying that is that the average velocity on the way up is greater than the average velocity on the way down. So let's look at the grading rubric on this one. So this is how you could have earned points on this part. Looks like you could have gotten 4 points, 5 points. You could have got a maximum of 5 points. 1 for stating that the time down is greater than the time up. And then notice the explanation part, you could earn just a point on these different parts. So notice it says 1 point for stating the magnitude of the acceleration while sliding up is greater than sliding down. So 1 point there. Another point for talking about the average velocity on the way up is greater than the average velocity on the way down. You could have talked about that the final velocity is less than that initial velocity due to friction. And then here we get sort of a loose point here where if you said everything else right, here's an extra point essentially. I don't really like the way that grading rubric is set up for that, but it looks like in physics there's some of those loosey-goosey points occasionally where if you got the other points, then we'll throw this one in too because you deserve it. But the main thing is don't just say time down is greater than time up. You've got to explain why. And do that in, 2-3 good sentences, and you're going to earn most of the points on these questions. Ms. Simons, do you have any just basic FRQ advice on either these QQT problems or the design and experiment questions you'd like to share?
Just kind of in general. So again, with the design and experiment, always start with your formula sheet. That's your vocabulary right there. Use that. And the other thing I would say with the design and experiment, if you go back and look at the PowerPoint presentation, that was question number 2, but nobody says you have to answer that as your second question. So I would suggest looking through all 5 questions before you ever start number 1. What are those questions? And just looking at those diagrams that they put the pictures, you can get an idea, oh, this one might have something to do with rotation, or this one might have something to do with conservation of energy or whatever. You already have a plan in mind. Figure out which one is the lab question. It's only going to be one of them, and make that your last question.
Yep. Because
it is so easy to spend more than 25 minutes on that question alone. So do the other 4 and then come back to the lab question, and whatever time you have left, do as much of it as you can to get as many points as you can.
Do you recommend skipping space in the answer booklet for that, or doing it at the end?
The space is provided in the booklet.
Oh, that's right. Never mind. You're right. It's not just a standard.
Right. So
the
space is already there in the booklet.
Yeah.
Just skip those pages and go on.
Yeah.
And speaking of space, if you find yourself on any question running out of room for writing your answer, if you flip to the end of your booklet, there are extra pages that are specifically left blank. It'll just say no testing material on this page or something like that. But they're numbered. Those pages are numbered in the book. Just say continued on page 17. And then write your answer there, and you can keep going without having to ask for more paper and get everything stapled in. And then the proctor has to write a report why you have things stapled in your book.
Yep.
When the people are grading your response, they can look at the whole book. So they'll see that note and they can flip to page 17 and see the rest of your response.
Good advice. Anything else?
Not really for me. You guys have any questions out there?
Don't be bashful. If you have a question, ask.
Yeah, now's the time.
So you're getting really close. You're down to what, a little bit over a week before your exam. So brush up on the things that you're struggling with. If you haven't checked out the College Board's review videos, you can go to YouTube and just put in the search advanced placement. They have an AP YouTube channel, and their review videos are really well done. They're about 45 minutes to an hour a piece, and you can find one on just about any topic that you might be struggling with. So I would say start there.
There are new videos in the AP Classroom site as well.
Yes, yes, and they're the same, right?
Some of them, yes, some of them, no.
Yep. And if you've ever tried flipping physics, if you want to laugh as you're learning something, I would recommend looking at Flipping Physics as well. That's
Yep.
another YouTube channel, and he does a really good job of explaining things.